this fifth lesson of chapter 3 of the course of basic geometry, two theorems are established. The first theorem shows the equivalence of the areas between a parallelogram and a triangle built between two parallel lines. The second theorem shows the Pythagorean theorem that establishes the relationships between the hypotenuse and the legs or catheti of a right triangle. In this first slide of this fifth and last class of chapter 3 of the course of basic geometry is presented a demonstration of the theorem that shows the equivalence of the areas of parallelograms and triangles constructed between parallel lines. Figure 3.25 shows the drawing of two parallel lines, AB and DE, constructed at distance h. In the lower straight line segment, that straight line segment AB is marked which will be the basis of the parallelogram ABCD and of the triangles ABC and ABE. The areas of the triangle ABC and ABE, as shown in the previous class for the acute and obtuse triangles, are given by the product of the dimension of the straight line segment of the base AB by the dimension of the straight line GH, that is the height, divided by 2. The parallelogram ABCD is composed of two identical triangles, ABC and ACD. These triangles are equal because the segments of straight lines AC and AD are parallel, and they are between two straight parallel lines. They have equal dimensions. In this slide, the demonstration of the theorem shows in the previous slide is continued. Figure 3.25 is shown again. Also, because the straight line segments AD and CB are parallel, and also because the straight line segments DC and AB are parallel, the segment of straight lines AB and DC have equal dimensions. As previously reported, it has been shown that the triangles ABC and ACD are equal because they have equal sides, and the sides AD and BC are parallel. Then, since the parallelogram is composed of the sum of the two areas of the equal triangles, the area of the parallelogram has double the value of the areas of the triangles. Therefore, we can state the theorem as: when a triangle and a parallelogram are constructed between two parallel lines and have the same base on one of the parallel lines, the parallelogram will have twice the area of the triangle. In this and next 6 slides, it will be presented a demonstration of the Pythagoras of Samos theorem. Pythagoras lived about 570 years before Christ. The proof presented here in this fifth class of chapter 3 of the course of basic geometry is based on the proof presented in the book Elements of Euclid of Alexandria, which lived some 300 years before Christ. Each slide shows figure 3.26, where the triangle ABC is presented with a square added to each of the sides of the triangle. Each square has a side dimension equal to the dimension of the side of the triangle to which it is added. Thus, you have three squares, ABFG, ACKH, and BCED. The area of the square BCED is equal to the sum of the areas of the squares ACKH and ABGF. Thus, the area of the square ABFG is given by the dimension of the AB side multiplied by the dimension of the same side AB. The area of the square ACKH is given by the dimension of the side AC multiplied by the dimension of the same side AC. Thus the area of the square BCDE is given by the dimension of the side BC multiplied by the dimension of the same side BC. Normally the statement of the theorem is as follows. The sum of the square of the dimension of the hypotenuse is equal to the sum of the squares of the dimension of the legs, or Catheti. In this slide begins the proof of the theorem of Pythagoras. Initially auxiliary straight lines FC, BK, AD, AE, and AL are drawn, with the straight line segment AL being parallel to the straight line segment BD. The BAC and BAG angles are right, that is, they have a value of 90 degrees. The segments of straight lines AC and AG are parts of the same straight line CG. The same is true for line segments AB and AG, which are parts of the same straight line BH. The DBC and FBA angles are right angles, then they are equal. By adding the DBC and FBA angles to the angle ABC, you have the angles DBA and FBC, which are equal, since the sum angle ABC was added at a right angle. The straight line segment AB is equal to the straight line segment FB. The same for the straight line segments BD and the straight line segment BC. Therefore, the triangles FBC and ABD are equal, because they have an angle and two sides with equal dimensions. The proof will continue with this new slide. The line segments BD and EAL are parallel. Using the previous theorem demonstrating this class of equivalence of areas of triangles and parallelograms constructed between parallel lines with the same base, we have the triangle ABD has the base BD in the parallel straight line BD and the vertex A in the other straight parallel line AL. The BDLM rectangle, which is a special case of a parallelogram, has the same base BD and the opposite side in the line segment AL. So by the mentioned theorem, we can say that the parallelogram BDLM has twice the area of the triangle ABD. Continuing on this new slide, the straight line segments FB and JC are parallel, because they are parts of the opposite sides of a square. Using the previous theorem demonstrating this class, the triangle FBC with the base in the line segment FB and vertex C in the segment of parallel line GC, and the rectangle FBAG, which is a particular case of a parallelogram, have the same base FB of the triangle and the opposite side on the parallel straight line segment GC, the parallelogram has twice the area of the triangle FBC. But the triangles FBC and ABD have the same areas, so the parallelograms FBAG and FBDLM have the same areas equal to twice the areas of the triangles FBC and ABD. In this new slide, the same process is repeated, and it shows that the triangles ACE and BCK are equal and have equal areas. The observation that the straight line segments CK and BH are on the opposite side of the square ACKH results that they are parallel. So the triangle BCK has the base CK on the parallel straight line CK and the vertex in the parallel line BH. Also the square ACKH, which is a particular case of a parallelogram, has the same common base CK of a triangle BCK. Thus, using the already mentioned theorem, you can say that the parallelogram ACKH has twice the area of the triangle BCK. Continuing in this new slide, the segments of a straight line CE and AL are parallel by the construction. The ACE triangle has the CE base on the straight line segment CE. The CELM rectangle, which is a particular case of a parallelogram, also has the common base with the triangle ACE and the opposite side in the straight line segment AL. Then, using the already mentioned theorem, we can say that the CELM rectangle has twice the area of the triangle ACE. In this last slide of this last class of chapter 3 of the course of basic geometry, the proof of the theorem of Pythagoras is finished. The ACE and BCK triangles have equal areas, so the CELM and ACKH rectangles also have equal areas. But these particular cases of parallelograms have twice the areas of ACE and BCK triangles. But the area of the BDEC square is the sum of the areas of BDLM and CELM rectangles. Then it was proved that the area of the square BDEC is equal to the sum of the areas of the square if BAG and ACKH.